All right, for this first example, you have an engine oil at 60 degrees, which flows at this upper surface, 5-meter long flat plate, whose temperature is 20 degrees. No? At this velocity, 2 meters per second. So determine the heat rate of heat transfer per unit width of the entire plate. Okay. So how do we do this now? No. So we need to first understand what should we do. No. First. So we need to find Q convective. No. So we need to know the area, the temperatures, and each. So as you can see, we already have the given. Actually, the area is just length times width. So this is per unit width. So we don't need to know the width. You have the given temperatures. We only need to find the H. So to find the H, you need to know the Nusselt number. No? So to find the H, you need the Nusselt number first. To find the Nusselt number, you need the Reynolds number, the Prandtl number, and to know what is the flow regime of this scheme. No? So actually, the direction should be this way. Yeah. So we need to first find the flow scheme, no? And to find the flow scheme, we need to find the Reynolds number. So to find the Reynolds number, that is just it depends on what formula you use. I will just use this very complicated, no? So rho VLC over mu, no? So LC here is the total length, which is 5 meter. So we want to find the Reynolds number at this length. So how do we find this now? So this should be at what, no? So the densities, everything here, and the viscosity should be dependent upon what, no? Upon the temperature. So you need to find first the TF, no? Which is just TS plus T infinity over 2. So we have a table here to find the densities and the viscosity of engine oil, but at what temperature, no? So we have 60 and 20 degrees here. So since this 60 here is the free steam temperature, this 20 here is the temperature of the surface. We have already a representation here. So we need to find that film temperature. The film temperature is so 60 plus 20. So this will be 40, no? 40 degrees Celsius divided by 2 pa. So at 40 degrees Celsius, you have this. Okay. Okay, so you have this. So you can actually find their densities. So finding the Reynolds number. Actually, you also have the Prandtl number as well. So you have the density, which is 876.0 times the velocity. So the velocity here is 2 meter per second. We have to take note of the units, but anyways, yeah, let's just write this for now. And then 5 meters. And then you have mu. So mu here is the dynamic viscosity, which is 0.2177. So analyzing the units here, this will be kilogram per cubic meter multiplied by meter per second multiplied by meter over. So kilogram per meter per second. So this should be dimensionless, no? So the numbers that we've encountered should be dimensionless, no? So cancel this, cancel um so this will become sige, this will cancel. So you have um uh over m here, so this will be upward. So this will all cancel. Okay. So we are good, no? So this is dimensionless. So everything will cancel out. We can find the Reynolds number. So the Reynolds number, let's have a calculator here. So you have here 876 times 2 times 5 over 0.2177. So you have 40,238. No? So 40,239 na lang. No? So as you can see, this is lower than 500,000 or 5 times 10 to the 6. Therefore, it is fully laminar. No? Okay? Fully laminar po yan. No? So fully laminar, Therefore, we should use the formula, no, of well, to find the Nusselt number average, you have 0.664. That's right. Always forget this, or 644 or 664. Oh, it's 664. That's correct. No, and then one half and then one third. Sorry about that. So RE 0.5 and PR one third. Okay. So we already know the Reynolds number. We just need to also find the Prandtl number. So for this given, the Prandtl number is 2000 pala, no? 2,962. Okay. So that is very high, no? So the Nusselt number here will be 0.664. Then you have 4239 and then raised to half or square root, no? And then Prandtl number of 2962. Okay. That is raised to one third. So the Nusselt number can be found. Where is it? Nusselt number is 0.664 times 4239, 0.5 times 2962 raised to one third. One third. Yeah. So the Nusselt number is 1912. So what 1912? So what does this mean, no? So I'll just say this is 1913. So therefore we can solve for the h, no? So sorry, I'll just write this down here. No, sorry about this. So nu is equal to HL over K, right? So we also need to find the K. So to find H, that is basically just K nu, K over L nu. So K over L, you have the thermal conductivity, which is there. Conductivity, so 0.1444 divided by L. So L here is 5 meters. And then the Nusselt number, 1913. Okay, so the Nusselt number, sorry, the H here will be solved as well. So 0.1444 over 5. Then times 1913. So you have 55.25. So 55.25. So the unit should be in watts per square meter Kelvin. Yan. Okay, so therefore you can solve for Q, convection, no? So Q convection is just H AS, diba? And then you have TS minus T infinity. Okay? So therefore you can actually it should be T infinity, no? It's hotter. So the convective coefficient will be 55.25. So 55.25. So the area is 5 meter by 1 meter, no? So per unit width. So that basically means just 1 unit width. And then 60 minus 20. So the answer here for the heat loss, or actually the heat gain. So 55.25 is 5 times 1. So there will be rounding errors now, of course. And then this will be 1150. So this will be 11,050 watts. Okay, so that's it. Okay, that's it.